Hello guys, today I wanted to make a video about Barlow Twins and I'm going to write it down on the screen. And so let's talk about what Barlow Twins is. And so Barlow Twins, it is a method of self-supervised learning, which I'll annotate with the word SSL. And it's a special type of self-supervised learning. It's called contrastive self-supervised learning. And so you might be wondering, what does contrastive mean? Well, it's in the title itself. Contrastive means what you do is you kind of check how similar something is or how contrasting or how different something is. And in this case, Barlow Twins checks how similar versions of the training data are to themselves. And I'll elaborate a little bit more on this. And so you might be asking, okay, what is a self-supervised learning used for? And so one practical use case for it is to do this thing called generating embeddings. So you might be wondering what embeddings are used for. And I'll give you an example. In some cases, you do not have enough data. One sec. Sorry, I'm going to make a correction. Self-supervised learning isn't only good when you have less data. It's good when you have a very little amount of labeled data and a lot of unlabeled data. So, correction. So what we do with self-supervised learning is we get these embeddings, as I mentioned, and these embeddings kind of are these values, these vectors, which are learned from the data, such that similar images, in this case if it's contrastive, similar images will get similar embeddings. And remember, these embeddings are just vectors. They can be vectors just, essentially a list of numbers, right? And so the thing about these embeddings is that similar images, I'm just going to write it down, similar images will get similar embeddings. So I'm just going to write it down. I'm just going to write something down. So these two images are similar, and their embeddings will be pretty similar as well. I'm just going to put some numbers, and these vectors have a very, very small distance from each other, right? The distances between are very, very small. And in some cases, actually in the real world, you'll have a lot more numbers than just 3, and your differences in distance might vary. But the point is, if we have images that are similar, our embeddings will be similar. But if our images are different, we will have different embeddings. As you can see, these two embeddings look much different than these two, right? And so that's the point of contrastive learning. And then you might be asking, okay, then what? Then we have these embeddings, and they're much smaller in size than the images in our data set. So if we give it to some other model, we give these embeddings to some other model, it makes it a little bit easier to learn from the data and do stuff like classification. So this model's performance would be higher than a model that just directly took the images in, because there's simply not enough images, right? And so that's the use case for self-supervised learning, to generate these embeddings. And so now you might be thinking, hey, what makes Barlow Twins special? Because if you're familiar with the machine learning community and the papers on arXiv, you would see a lot of self-supervised algorithms. For example, there is SymCLR and NNCLR, and there are actually a lot more. But what distinguishes Barlow Twins from the rest So that's a good question. Well, let's talk about the problems with these approaches. So you remember, the point is to generate these useful embeddings, right? But what happens in these previous algorithms is that the embeddings do not carry much information about the data. Because as you remember, all you need to know is that, right, all the model needs to do is to make similar images have similar embeddings and different images have different embeddings, right? And so you're basically it's basically that's just like a yes or no question. Are these two images similar and are these two images different? Now that's not what we want. We want the embeddings to capture the essence of the image. But what's happening is that the embeddings are they're doing the bare minimum. They're getting the minimum amount of information about the images. And so if we give these embeddings to a new model, the model will not learn very well from them. And let me just illustrate an example. Okay, let's say we have two images that are the same, as mentioned, and let's have two images that are different. There are no two shapes which are more different than a circle and a square. Right? So these two images, they're the same. But in this conventional methods, the algorithm would just put like ones or something. Ones for similar images. And something like a zeros for images that are different. This does meet the task. It does make similar embeddings for images which are the same and different embeddings for images which are different. But these don't really help the model. If you were to give these sequence of ones and zeros to the model, it will not be able to classify a mountain versus a circle versus a square. And so, that's not what we want, right? And so let's talk about how Barlow Twins, so this is why we need Barlow Twins. So Barlow Twins is basically designed to combat this problem and we call this repetition and this lack of information, we call it redundancy. And so previous algorithms, to solve this redundancy problem, you had to tweak the hyperparameters like the learning rate, batch size, so on and so forth. You had to very carefully tweak them so that the model would not do this. But Barlow Twins, as mentioned, Barlow Twins is designed to remove redundancy. We want to remove this. And so let's talk about how this works. And so Barlow Twins also prioritizes this redundancy in its loss function. And so let's do a little bit of a formal explanation for these methods, okay? And so let's use some vocabulary terms. Previously, I said images which are similar have similar embeddings. Images that are different have different embeddings, right? And so instead of repeating that again and again, I'm going to be using the word invariance or invariant. We say these embeddings are invariant. And so that's what we want. And so that's it. And now let's talk about the model architecture of Barlow Twins. It's actually a really, really simple process compared to these other methods. And so that gives you some benefit when you're training it as well. So let's talk about what happens. So this is self-supervised, so we don't have any labels, right? Right. So what happens in Barlow Twins, right? You have a few images which are labeled and a lot of images that aren't. So we want to focus on those unlabeled images. And in self-supervised, what you do is you kind of turn this unsupervised thing where you have just a lot of just plain images into a supervised problem. And in this case, what you do is you take this one image, which I'm going to call X, and I'm going to distort them into two other images, which I'm going to call Y, A, and YB. So I'm actually looking at a reference image while talking to you, and I'll share that reference images with you in post. Anyways, we distort these images by augmenting them. What we do is we apply these transformations like brightness, saturation, or we move the image around. So we have images which come from the same source, but in the end look different, right? And then what we do is we have the same model architecture, I guess. We have this model architecture which takes in these images and it generates embeddings, which we're going to label as ZA for this YA, and write it down, ZB for these, right? And so these are our embeddings, and this is the same model. We're just checking the model's embeddings for this first version of the distorted, first version of the image, and the second version, right? So now, this is like the unique part of Barlow Twins. Previously, what other methods would do is we just compare the similarity of these embeddings by using something like cosine similarity, or even a simple mean squared error. And obviously, if these embeddings are more similar to each other, we would get a value closer to 0. And if they're more different, we'll get a higher value. And in Barlow Twins, we have that same notion where we do measure similarity in that form. And that similarity number will be like our loss function, right? But this is where it gets special. What we do is we take these two representations or embeddings, right? And what we do is we make a little cross correlation matrix. And if you're familiar with time series, you probably would have heard this word before. But what this does is it checks, I say, the correlation, or I'd say similarity, the embeddings, and then you have each value of your embeddings here, like the 0th value goes here, and then the first, and so on and so forth. So you have ZA's values on this axis and ZB's values on this axis. And so what you do is you kind of check the similarity. I guess you take the similarity for each, and it's actually a formula to make a cross correlation matrix. It's actually really simple. What you do is you take the transpose of this first prediction, so transpose, and you matrix multiply it with the second one, and you divide it by the batch size. And so let's talk about how multiplying these different embeddings can get you a cross correlation matrix. And so to do that, let's first talk about the dimensions of these. The dimension of this one will be the number of embeddings, which I'll just mark as something like F or something. Or no, I'll put like, G for this by 1, because we're assuming that it's just a list, right? And then this one will also be G by 1. So, sorry. I need to change this, I think. One sec, this will be edited in post. Your predictions will actually be flipped like this, sorry. So it'll be 1 by G. This is the dimension of your first embedding, and then your second one will also be 1 by G, right? And so what we do is we transpose this, such that now the dimension of this is G by 1, and we multiply it with the dimension of 1 by G, right? And so in the end, we get an array with size G by G. And that is the dimension of the cross correlation matrix. So actually, if this doesn't work out, skip this in post. And I'm also going to show you a little matrix multiplication. Let's just say we had two values as our embeddings, A, B, and here we also have two values, C and D. In this case, our batch size is 1 because we only have one set of embeddings, right? And here we also have only one set of embeddings. But this process works if you have more batch, even if your batch size is a bigger number. And you can try doing the math yourself and you'll actually see, because what happens actually is that it sums up all the cross-correlation matrices it multiplies in the batch. And if you do the math, you'll see that that's what happens. Anyways, let's do this algorithm. Let's do this thing. So we transpose it and we get A by B times C by D. This is a 2 by 1 matrix times the 1 by 2. So in the end, our cross-correlation matrix should be 2 by 2, right? So let's draw our matrix, I guess. And so let's do the matrix multiplication. It'll be A times C, A times D, B times C, and B by D. And then we divide all of this by the batch size, and the batch size is 1, so this will be our cross-correlation matrix, right? And so that is how the process works, I guess. And so this is the equation for the cross-correlation matrix. And then in the end, when we have representations which are similar, our cross-correlation matrix will actually look like an identity matrix. And so remove this in post if this doesn't work out. Let's say we have 1, 2, or something. No, I'm going to use decimals. 0.3, 0.5, and 0.31, and 0.49. So these are relatively similar. So we're going to transpose it again. Transpose this first one, 0.3 and 0.5. Right, and so let's matrix multiply them together. We write it down on the screen. Okay, and so I'm going to write it down. 0.3 times 0.31, 0.3, 0.49, 0.5, 0.31, 0.5, 0.49, right? And so I have my trusty calculator, and we're going to just test it out and see if this works. You will get 0.09, 0.15, 0.16, and 0.24. Right. And you might think, hey, this does not look like an identity matrix, even though our embeddings look similar. Well, here's the thing. This cross-correlation matrix, it doesn't just measure the similarity. It measures how redundant it is. As you can see, the differences between 0 and 5 aren't as much. So we want to be as clear as possible. We want our embeddings to be as clear as possible about our images, I guess. And so 0.3, 0.5, they're just I think this is my guess, they're way too similar. We want there to be that kind of contrast, I guess. And so when that happens, we'll get a cross-correlation matrix, which looks like an identity matrix, which is what we want. Now, let's look at our graph. we make this cross-correlation matrix, but then we need a loss function, which is a number. Or if we have many images in the batch, it'll be a list of numbers, right? Or actually, no, it'll just be a number. And so we got to turn this cross-correlation matrix into a number somehow, right? And so let's talk about how we turn this cross-correlation matrix into a number, right? So we have this matrix. We have a bunch of values here, right? And so what we do is we take two parts of this matrix. We take the invariance term. The invariant, remember, invariant means similar embeddings are similar, different embeddings are different. And so that invariance term will be this diagonal of the matrix. Because if you know about correlation, the values in the diagonal are supposed to indicate how correlated or how similar the embeddings are towards each other. So we take the diagonal as our invariance term, and the rest is our redundancy reduction term. And so you might be wondering, why do we need to do that? Why do we need to take these parts as a redundancy reduction term? Well, if there are parts of the embedding which are correlated with other parts, that means that they're doing more than they're doing too much. They're not doing their job, which is to give valuable information. They're mixing up parts, and they're being kind of useless. And so we want these parts to be zero, to just emphasize that redundancy reduction, to show that these embeddings are correlated, right? So let's talk about how we do that. So first we take this term, invariance term, you can call it our diagonal, and what we do is we want these values will ideally be from 0 to 1, right? And if they're 1, that's good. If they're 0, they're not. That's not so good, because that means the embeddings are not correlated. And so how do we flip it around, where if our value is 0, it's good, and 1 is bad, right? How would we do that? Well, one way we could do it is we could subtract 1 on both sides. 1 minus 1 is 0. That's good. 1 minus 0 is 1, which is bad, right? So what we do is we take 1 minus all the values in the diagonal, and we square them to kind of emphasize our differences. And also, if we have any negative numbers, we will make them positive. So our loss will not suddenly decrease, even though it shouldn't, right? So that's our invariance term. So now let's talk about what we do to our redundancy reduction term. Well, what we do is we just square them. We square the values in the redundancy reduction term, because if the differences are big, when we square them, they'll become even bigger. And if we have any negative values, again, they'll become positive. We'll call this redundancy reduction term off diagonal. What we want to do is we want to square this value. And then now, because it's still not a number, right? We still have these arrays. We take the sum of all this, and we also take the sum of this, and we add them together to get a number. And so this number will be our loss. And so that's how the Barlow Twins works. And so I will be giving you a little coding demonstration later on. But first, let's go more in depth about the network, right? I showed you this diagram, which is kind of the training process. But let's talk about what this network is, okay? And 1 second. This model, if I'm getting it correct, this model is made of a projector network, I totally misspelled it. Projector network. And this projector network takes values from an encoder network. Take values from here, and then we get our embeddings. And so let's talk about what this encoder network is. according to the paper, it is a ResNet Net 50, but I found if you use datasets like CFAR10 or any smaller dataset in general, it would be better. I found result-wise that a ResNet 34 would be good, and I think in general it is any kind of ResNet or anything. And so now let's talk about what this projector is. This is arguably pretty important. Well, this is important, not arguably, because it generates the embeddings from these encoder outputs. And so it's actually pretty simple. What you do is you pass these outputs through a fully connected dense layer, and then you pass them through a batch normalization layer where the weights are normalized. You pass it to a ReLU activation function, and then you repeat that, I believe, I think twice. You do it twice. I think you can actually change this number. I think in the paper it is 3 times, but I'm not sure. But I found with these smaller data sets, 2 times is enough. And anyways, at the end, you concatenate this to a little dense layer. And so that will be our embeddings. And so now I think we have enough information about how this Barlow Twins works. And so I'm going to go over a little Keras.io example, which actually I made, which illustrates this in code. And so I'll be there with you shortly. So hello guys, here I am. I am at Keras.io/examples. I'm looking at their examples, and I'm looking at the Barlow Twins. As you can see, this has been created by me and actually modified pretty recently by me. I recently made this demonstration, but I'll get to the gist of it. And as you can see, this is the image which I promised to show you. We can see our source image, and we can see that we make 2 different augmentations of them. And then we pass them through our identical model, and then create embeddings, and then use a cross-correlation matrix, and then use our loss function, which turns this value into a number. And then we pass that back through backpropagation, right? And so let's scroll down and let's actually look at the important bits. So these are some important imports, and as you can see, I've included a few optimizations to make it faster, and I found that they really help. Here I'm using CFAR10, and as you may remember, I mentioned that I found ResNet 34 and I say two batch norm two dense batch norm ReLU intermediate tray layers in the projector network to be the most helpful, I guess. And as you can see, my batch size is 512 and my image size is 32 by 32. That's expected. And so if you remember in the diagram, we have to augment our 2 images. And so this is the code, I guess, to augment them. And as I mentioned here, one unique feature of Barlow Twins is that sometimes augmentations probabilistically occur. So for example, we don't want all the images to become grayscale, but we only make like 20% of our images grayscale. And that's kind of the gist of it. This is kind of what this augmentation stuff does. So you can view the class itself later, but as you can see, I've used tf.image utilities. And I've actually heard that that there are some good alternatives out there that are being developed, like I've heard Keras CV, which is a pretty interesting image processing library, which I can just search right now. This is it. It is Keras CV. This is the GitHub link. And these are the contributors, and I would suggest to check them out here. And this is basically probably the alternative to tf.image, which I probably have to use in the future. But for now, I'm using them. And let's just view what our augmentations are. The way we are augmenting our images is that we're either making them grayscale, we're adding some color modifications, we're flipping them, randomly cropping them, and we're doing solarization, what happens is we take these extremely abnormally low pixels and then we make them extremely bright pixels. And so that's actually a camera defect that occurs, but it's really good for augmentation in this case. And we also got blur. So let me scroll down. And then this is our data loading architecture. And as you can see, this is our code to present, but as you can see, we get two different types of augmentations of the same image. And you can see this image and this image, they're the same reference image, except one's more distorted than the other. And I've actually noticed that some of the images can be extremely dark or extremely light, but actually I don't think that's affected the accuracy as much as one might expect it to be. And so here is the pseudocode for the loss function, and here's a little reference. And this is the loss function, as you can see. What happens is we normalize the values, then we make a cross-correlation matrix, and then convert that to a number. That's what we expect. And oops, that's not good. The phone just went sideways. Anyways, this is our model architecture, and I used this site. Looks like it's duplicated twice, but I used this website, which gives a good insight into how to make your own ResNet 34. And it was made by Yashowardhan Sinde. And sorry if I mispronounced your name, but that's who this website was made. Who made this article, not the website. And this is the important part. This is our projector network. So here we define our encoder network, which is our ResNet backbone. And then we attach these dense batch norm ReLU, and as you can see, we only have 2 layers. I think originally I had 3, and in the paper they have 3. But in this case, I chose 2. And then this is our training loop. We just take the gradients, we just take the loss and then apply the gradients. It's pretty simple. And we use, in this case, we are going to use the LAMB optimizer. In the paper, they used LARS, L-A-R-S. I couldn't find that in any TensorFlow package, but here I found this LAMB, which is the closest thing. It's actually an improvement on that LARS optimizer. And I found that it actually helps the model converge much, much faster than Atom, which is the conventional optimizer used in these scenarios. So as I was saying, this is our training. As we can see, the loss went down, which is good. That means the model is learning accurate embeddings. And now this is how we evaluate, because it's pretty hard to figure out if the model did a good job. So what we do is we basically freeze this network such that its embeddings will be identical to the ones at the end of epoch 160, right? And so we take these embeddings and we freeze them, and then we just attach it to a dense layer. This dense layer, then we train this model on this, I guess. And in the end, so this model just has to learn the weights for this dense layer. So really, this BM.model, our architecture, does most of the heavy lifting. And so this is a proof of concept to see if the embeddings work. And we also check the accuracy. And if the accuracy is, I say more than 10%, if we have 10 classes, and so on average 10%, then we know that we're getting good results. And actually, in this case, we get like 69% in the training. And in validation, we get up to 68.2, I guess 68.3 approximately, which is a really, really good figure. That's much more than the 10%. And actually, if you had a little bit more data that is labeled, or if you had more dense layers or more parameters or whatnot, this value would go higher. And actually, you could make a functional trainable model with very less, I'd say, data compared to what you traditionally need. And so, as we mentioned, we talked about the use cases, and we said it could be used in semi-supervised learning. Actually, this is the actual term for what main use case I talked about. And as you can see, you use the Barlow Twins on the unlabeled data, and then you do secondary training with our labeled version. So here are some references. This is the paper. I'll go to it. This is the abstract. It's made by these authors. And here's the original PyTorch implementation on GitHub. And this is a really great implementation by Saik Paul, a really good contributor to the Keras IO repository. And you can see his example. And I believe he used a ResNet 20. And so his accuracy, I think, was 62%, which is a little bit less than our 68%, but that's because our architecture was, I'd say, a little bit perfect for this job. And of course, thanks to you for writing the article, writing the ResNet 34 article. And so thank you guys for viewing this coding example. This is the notebook. It's keras.io/example/vision.barlowtwins, and I'll include references in the description for you. And so thank you a lot for viewing, and yeah.